Thank you, thank you. Let me take the motion of center of mass. Yeah, let me assume two particles of mass m1 and other the m2. They are lying in a plane. You have to solve it. I just have an idea. You solve it, or later on I'll update it. I'll solve and update it. Let me introduce the idea of motion of center of mass. These are the position vectors of the particle. So what is the equation? We'll write it. RCM bar equal to m1 r1 bar plus m2 r2 bar by m1 plus m2. If any one particle or both the particles, if they are moving, if they are in motion, then what will happen to that m1 and m2 vector? What will happen to that r1 r2 bar? I'll displace it, or let they be in motion. If they're in motion means r1 bar r2 bar position will change with the time. So I'll differentiate this. If I differentiate, I'll end up with VCM equal to M1 V1 bar plus M2 V2 bar by M1 plus M2. This will be the velocity of center of mass. So let the velocity of the particles, let it be V2. Velocity of this particle is V1. Where the center of mass, let M2 be heavier than M1. So the center of mass of system should lie somewhere here. Velocity of center of mass will be directed in this way. As the particle moves, even the center of mass is also going to move. Due to some force will act on a particles. Due to that force, what will happen to the velocity of the particles are going to change. M1 dv1 by dt, M2 dv2 by dt by M1 plus M2. Correspondingly, the velocity of center of mass is also going to change. So this should be equal to ACM, M1 A1 bar, M2 A2 bar by M1 plus M2. What is ACM? Acceleration of center of mass of system. What is M1 plus M2? Total mass of system. So this I can also write by M. So this will become MACM equal to M1A1 plus M2A2. What is M1A1? The force acting on the particle 1. So let me, for our convenient, I'll show it like this. What about, let it be F1. So what is the force acting on the particle 1? Let it be F1. And the force acting on the particle, let it be F2. And what we are getting, ACM. So what are F1 bar plus F2 bar? It is the resultant force that is acting on the system. So this will call F external. This is nothing but Newton's second law, no? So when the center of mass will accelerate, when the system is acted upon by net external force. What are F1, F2? Forces acting on individual particles. The resultant of that is what? F external. The resultant force acting on particle 1, F1. F2 is what? The resultant force acting on particle 2. The vector sum of that resultant force, the individual force acting on particle will be the net external force and ACM bar equal to. So therefore here afterwards, the how to describe the motion of a system. There are two approaches are there. Individually calculate force acting on each particle, calculate acceleration of the particles. Okay, that one here. Individually calculate force acting on each particle. I think I'll write it here separately. I'll calculate force acting individually on each particle. Then I'll calculate acceleration A1 and A2. Then I know mass M1, M2. I'll substitute, I'll get acceleration of center. This is one approach. What is the other approach? Directly let me go for the net external force acting on system and I know mass, I'll get acceleration of center of mass. I'm going to say approach. I think this word is very important. Two approaches are there. How to calculate acceleration of center of mass. This is the first approach. So what is the first approach? The first approach is this one. This is the second approach. Now it's a very good conceptual thing. So rather than discussing much on theory, let me take examples itself. It will be very easy for you. In the first approach, what we do, you calculate force acting on individual particles, individual parts of a system. Here, particles I took. It can be even the blocks or segments of system. The force acting on individual parts of a system. You can M1, M2, you can also call it the parts rather than particles here. Because when we go for wedge constraint, I'm going to take same examples here. So what is the method? Calculate force acting on individual parts of a system. Calculate acceleration A1 bar, A2 bar. Use this formula, you'll get acceleration of center of mass. This is the one approach, first approach. What is the second approach? Calculate the resultant force acting on the system. What is F external you should call? Net external force acting on system. So calculate net external force acting on system by total mass of will be acceleration. Now you have to ask a good question to teacher. So which is very easy. It depends upon the situation. It all depends on situation. Sometimes tracing out net external force will be very difficult. Sometimes what happens, the tracing out means deciding net external force on system will be very difficult. So bring this one. In some situations, the net force is very easily available. So take help of this one. So this is what actually now say like here we are in a position to define now external and internal forces. Already we had in laws of motion some small idea, but here we are going to say clear-cut idea of which is external force acting on system, which is internal force. So till then I should not talk about internal external. Now I can talk I am in a better position to talk about internal external. Next again, what are the things? Suppose if net external force acting on system is 0. These are the numericals. What our numericals will be? Newton's second law only, Newton's laws only, we are exclusively writing in some systematic order here. If net external force acting on system is 0, and if center of mass is at rest, center of mass, I'll write COM is at rest. What will happen to center of mass here now? If net external force 0, so what is the immediate conclusion? ACM 0. If ACM 0, if there is no acceleration, so velocity of center of mass will be 0. Then what happened to center of mass? Will retain its inertia of rest. Center of mass retains inertia of rest. What will happen to delta RCM? Delta RCM will be 0. Change in position of center of mass will be 0. Or no change in position of center of mass. No change. You have so almost around 20 numericals are there on the first condition what I have put. 20 numericals. So what you have to do, you are supposed to identify in a system net force 0 or non-zero. This is the thing. Next again, second situation. If net external force is 0, center of mass moving with velocity, center of mass is having some velocity or having some initial velocity. What should happen? ACM is 0. What should happen to VCM? Will it be non-zero, no? Delta VCM will be 0. Will I agree? With what velocity the body is moving? If net external force is 0, then if body is having uniform velocity motion, it will continue its uniform velocity motion. Same thing with center of mass also. VCM will be non-zero, delta VCM will be 0. Are you able to understand this? What will happen to delta XCM? Delta XCM or delta RCM? Yes, as the center of mass is having uniform velocity, the position will shift. No? the center of mass will get displaced here. The third one, if net external force non-zero, center of mass at rest, let me take it, initially at rest. Some are asking is initially at rest. Initially moving with velocity. Some are asking this clarification. Okay, I just put it everything in order. Okay, now if net action for zero, center of mass is initially at rest. What should happen to acceleration of center of mass? Non-zero. Velocity of center of mass non-zero. Center of mass starts or delta VCM, better you write. Velocity starts increasing or varying, then position of center of mass is going to change. So what you have to check it now, whenever you get any system, check what is the state of the system. Is it rest or in motion? Yes, if it is at rest, net external force zero, then you can pick up the condition one. Net external force zero and the center of mass is having uniform velocity motion. Center of mass will continue its uniform velocity motion, but there will be change in position of center of mass. Now you have to ask questions of why you are already laws of motion we have discussed. What is necessity of center of mass? Again, our preparation is for what, like rolling mechanics, rotation mechanics, and collisions. In collisions, what happen? If you do problem in center of mass frame, calculations can be minimized. That is the purpose of why we are introducing this concept of center of mass here. So the first approach, second approach. So let me give one very simple problem